All right, let's take a look at friction when we have an angled force, like a push or a pull at an angle. We have two situations, one where a person is pushing down at a degrees 25 degrees below the horizontal and then pulling up 25 degrees above the horizontal. If we're given the applied force, the magnitude here, and the mass of the block, and the coefficient of kinetic friction, can we calculate the kinetic frictional force for each scenario? I'll begin by drawing an interaction diagram and force diagram for this scenario on the left. Pause the video, take a moment, and see if you can do this yourself before moving on. All right, I've gone ahead and shown the normal force from the lake pointing up on the block, the gravitational force from the earth pulling down on the block, the applied force in the direction it was shown, so in this case 25 degrees below the horizontal, and the kinetic friction force pointing to the left. It wasn't given, but in this case, assume that the ice block does begin moving, that it does exceed the force of static friction. And in this case, I'm showing the kinetic frictional force to the left because the block will be moving to the right. And again, friction is always opposite motion. Now, we have an angled force here. This F applied force is at an angle, so it's important to split this into X and Y components like so, right? I can also write out the expression for these because X is horizontal. This is the adjacent side to the angle we were given. That will be the hypotenuse times cosine 25. And then the Y component, or the opposite, would be 200 sine 25. Now what I'll do is I'll redraw my force diagram showing these components instead of the angled force, right? Always important to do when we have angled forces. All right, I've redrawn my force diagram, and I've made it very clear that my frictional force is less than this applied force in the x direction, right? Because the block should be accelerating to the right. I've also made it very clear that the gravitational force is not equal to the normal force, right? It is shorter. The normal force must be equal to, right? This force, this upward force, must balance by both of these downward forces. So I know that the gravitational force is not equal to the normal force in this situation, which is what I've been talking about. So let's take a look at the sum of forces in the x and y direction. Again, we're solving for Fk. And remember, the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So if I knew the normal force, I would be able to get my force of kinetic friction. So in this case, what I'll do is I'll solve for the sum of forces in the y direction. I'll get my normal force, and I'll use that for my kinetic friction force, just like in our previous examples. Let's do that now. So again, I know that the normal force, if I call it positive, minus the force of gravity on the block, or the block's weight, minus the y component of that pushing force, will be equal to the mass of the block times the acceleration in the y direction, but the acceleration in the y direction is 0, so that'll be equal to 0. Therefore, my normal force is equal to the weight of the block, right, its force of gravity, plus 200 sine 25. And I know that this will be equal to mg plus 200 sine 25, where m is the mass of the block. Plugging all my values in, I will get the normal force is equal to 45 kilograms times 9.8 meters per second squared plus 200 sine 25, which I'll approximate in my calculator. And that will give me a normal force of 525.524 newtons. Again, I'm using many digits here because I'm going to use this for calculation. If I were doing this, not in a video, I would be using my calculator and I would be storing values to make it as exact as possible. So then I'm going to come back here on the left and then say that since the force of kinetic friction is equal to the coefficient here, which is 0.03, times this normal force, 525.524, then the force of kinetic friction in this case will be equal to essentially 15.8 newtons. So I just want to point out that in this scenario, again, the normal force was not equal to mg, right? It had something to do with gravity, but it was not equal to the gravitational force, right? And therefore, when you're solving for the normal force in these problems and you have angled forces, do not just say Fn equals mg, right? You've got to solve for the sum of forces in the y direction. Once you've solved for that, once you have a value for the normal force, then you can get your frictional force. Now, I'm going to repeat this process for the block on the right, keeping in mind that it is a very similar process, although in this case, I'm going to have my y component of that force pointing up instead of down, right? The x component will be the same. It'll be 200 cosine 25. So I'm going to skip a few steps, but show, again, the same process here on the right-hand side for the pulling of the block upwards. All right, I've drawn in my redrawn force diagram with the angled force split into components. If you're not convinced, if I were on this diagram to show you, this would be the applied force in the x direction, and this would be the applied force in the, bad color there, in the y direction. There we go, better. And I know that this is going to be, again, 200 cosine 25, and this would be equal to 200 sine 25, but it's pointing upwards, so it's going to show up on my diagram in the upwards direction. In this case, it's working with the normal force against gravity. So when I write out my force balance in the y direction, it'll look a bit different. So in this case, the normal force plus that y component, they're both positive in this case, they're both pointing up, minus Fg would be equal to may, but ay is 0, so that's just equal to 0. So then when I try and solve for my normal force this time, I'll get a value like this, 356.476 newtons. And again, I can use the same expression where the force of kinetic friction is equal to the coefficient of kinetic friction, 0.03, times the normal force, which in this case is 357.476. That'll be equal to, and I'm sorry, this is actually a 6 here. 356, there we go. There you go, like it never happened. And this is equal to 10.7 newtons. And so it should be interesting to see here. When we're pulling up on the block, right, the normal force is smaller like we might have expected. But that also means is the frictional force here is also less. And that should make sense, right? Friction, remember, is proportional to the normal force. Friction is about interaction between two surfaces. So when we're pulling up on the block, we're decreasing the strength by which the floor, or the lake in this case, interacts with the block. But in this case, the block's still on the floor. It's just that it's not interacting as strongly with the floor, so that my frictional force is also less. So hopefully that makes sense conceptually as well. All right. So for these problems, again, same process as always. Just make sure you split your angled force into components and don't just assume that Fn equals mg. That will not be the case in every scenario, and these are scenarios where that is certainly not true.